Hello and welcome to lesson number 28, Sums of Finite Series. Before we start off the lesson, the very first thing we need to talk about is going to be the notation that we're going to be using in this lesson. For this lesson, we're going to be using the standard sigma notation that we use in mathematics. To learn sigma notation, it's quite easy. We just have to learn 4 basic concepts. They are the concept of the sigma itself, the thing that we put below the sigma, the thing that we put above the sigma, and the thing that we put to the right of the sigma. The thing that we put below the sigma is representing the starting index of a counting variable that we use to count the number of times we add something together. Usually this variable is going to be either I or R. In our case, let's say R, and we say R equals the starting value of our indexing variable. Usually we can find our functions to be of the form starting from R equals 1 and going upward. However, of course, R could be any starting value at the start. Similar to this, above the sigma, we write the ending index, usually written as n if we don't have a specific value. What this is representing is the very last term that our counting variable will reach. So in this case, our counting variable is going to jump in steps of 1, as in integer steps, starting from r equals 1 and ending at r equals n. So when we are doing a summation, the different number of values that our counting variable is going to get is going to be the values 1 and then 2, 3, 4, 5, 6 and so on until we get to r equals n. So we are going to have n total additions in this sum here. If we had different starting variables or ending variables, we would of course have different total number of summations being done. However, in this case we can see we start at r equals 1 and end at r equals n. This can of course be flexible. We could start counting at 5 for example. But usually you will get summations that are starting with r equals 1 and ending at some r equals n. Now finally, the most important element, the thing that's there to the right of the sigma. The thing that's there to the right of the sigma is the thing that we're actually summing together in each of the iterations of r. As in, when r is equal to 1, we have one sum of the thing on the right. When r is equal to 2, we have another sum of the thing on the right, and so on and so forth. However, this thing on the right is usually a function of the counting variable. It could of course be a function of something else, or it could be just a constant. However, usually the thing that we're adding together changes with our counting variable. I'm going to represent that with u of r. So now here u of r is changing with the value of r. If we consider this summation as a whole, what this summation is representing is the value of u r when r is equal to 1 plus the value of ur when r is equal to the next value, which is going to be 2, plus the value of ur when r is equal to the next value, which is going to be 3, and so on and so forth, all the way up to u of r when r is equal to n. So considering that, this sum is going to give us all the values of ur starting from the value of the indexing variable r being equal to 1, so u1, plus the next value of r, which is going to be r equals 2 of ur, so that's going to be u of 2, plus the next value, which is going to be u of 3, plus and so on, all the way up to the very final term where our counting variable is going to be equal to n, and therefore the value on the inside that we're going to be adding together is going to be u of n. So this is how this summation notation works. It's quite simple. You have 4 basic elements. They are the sigma itself, the number below it which indicates where your counting variable starts, the thing above which indicates where your counting variable ends, and the thing to the right which indicates what you add up as your counting variable varies from the starting index to the ending index. It should be noted here that this is an integer operation. It works on integers. Due to that, you cannot have your ending variable minus your starting variable being a non-integer. Because if that was the case, then you would have like a non-counted value that you would reach in your sigma. We cannot have that. So therefore, the difference between your ending value and starting value must be an integer. Now that we have that out of the way, we know what the sigma notation means for integer values of the difference between our ending value and our starting value. Now that we've done that, let's move on to some rules that we can observe with this sigma notation. The first and most important rule that we can observe with sigma notation is this. If you have the sum, let's say we put the ending limits and starting limits in, of two terms, let's say u of r plus V of R added together and then sigma'd. This is equivalent to having the sigma from R equals 1 up to n, same exact bounds, of U of R first, and then adding to that the sum from R equals 1 up to n of V of R. This can be easily observed if we start writing down each of these sums. For the first one, the sum here is going to be all the values of UR plus VR for the values of R going from 1 up to n. So the left side sum, the LHS, is going to be equal to U of R plus V of R when R is equal to 1, which is going to be U1 plus V1 plus the values of U of R plus V of R when R is equal to 2, so U2 plus V2 plus the next values, which is going to be U3 plus V3 plus and so on and so forth until the very last terms, which are going to be the values of UR plus VR when R is equal to n, which is going to be UN plus Vn. Now considering the right hand side, on the right hand side what we would have is all the sums of U of R for all of these values of R, which is going to be U of 1 as we saw earlier plus U of 2 plus U of 3 plus dot 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 all the way up to U of n, and then we need to have the sum of all the terms of V of R for those same R's. So that's going to be V of 1 plus V of 2 plus V of 3 plus and so on all the way up to V of n. If we look at these two terms, we can see that the sum on top has the U1 plus V1, the bottom also has U1 and V1. The next term here in the above sum on the left hand side is U2 plus V2. The bottom sum contains U2 and V2, and if we keep doing this, we can see that both of these sums are equivalent to each other. This is a common identity that we will commonly use to simplify complex sums into simpler components that we can solve individually. So here we can see, as like a rule, we have a sum and we are summing it, and it's equal to two different values summed together. So if you want to be a little humorous, you could say that the sum of the sums is the sum of the sums. That didn't really make much sense if you say it like that, but here you can see in this identity that's exactly what's happening. If you say it like that, you might even see exactly why it's true. So that's our first identity. Our second identity is going to be that if you have the sum from R equals 1 to n for simplicity of a constant k times the function U of R, this is equal to the constant a times the sum from R equals 1 up to n of that function. Once again, we can see why this is true if we simply write these two out. If we write the two out, on the left hand side what we have is k times UR for every single R from R equals 1 up to R equals n. Therefore what we have is KU1 plus KU2 plus KU3 plus so on and so forth until the very last term, which is going to be KUN. As for the right hand side, RHS is going to be K multiplied by the sum of U of R. The sum of U of R from R equals 1 to up to R equals n is going to be U1 plus U2 plus U3 plus dot 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 all the way up to U of n. By the distributive property of multiplication, we can see that this thing is going to give us KU1, this bit is going to give us KU2, the next bit is going to give us KU3, so on and so forth until KUN. So therefore, each term in the above series is there in the below one, meaning they are equal. So therefore, for k being a constant, k times the function sum is equal to k times the sum of the function. For our final identity is not so much an identity as it is a cautionary tale for when you are simplifying these kinds of things. If you consider the sum from R equals 1 up to n of U of R multiplied by V of R, this is not necessarily equal, this is not necessarily equal to the sum from R equals 1 to n of U of R multiplied together by the sum from R equals 1 to n of V of R. This is obviously not true if you just write them out. However, some people might accidentally make this substitution. You should note this does not work. We can see why this doesn't work most of the time. Well, pretty much all of the time. Like, you have to have a very rare circumstance for this to be equal. However, if we just take a look at the terms that are involved, we can see why this wouldn't be true in general. If you consider the left hand side LHS, the LHS is going to be the terms u of r times v of r from r equals 1 up to r equals n. Therefore, the terms that we have here are going to be u of 1 times v of 1 plus u of 2 times v of 2 plus u of 3 times v of 3 plus dot 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 until the very last term, which is going to be u of n times v of n. And for the right hand side, we can see the right hand side is the product of two sums. It's the product of the sums which are going from u of r from r equals 1 up to n and v of r from r equals 1 up to n. If we write those out, we can see that these two sums would be equal to, starting from the first sum, it would be u of 1 plus u of 2 plus u of 3 plus dot 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 until u of n, and the next sum would be v of 1 plus v of 2 plus v of 3 plus dot 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 all the way up to v of n. Now if we consider this thing here, we can see that at least all of the terms that we require in the above series are there in the below series. We can see that you have u of 1 v of times v of 1, we have u of 2 times v of 2, we have u of 3 times v of 3. All of the terms in the above series will occur if we do this multiplication, because if we do the multiplication and distribute everything, u of 1 will eventually be multiplied by v of 1 and we'll get u1 v1. u2 will be eventually multiplied by v2 and we'll get u2 v2 and all of that. However, we get a ton of unwanted terms. If we look, we can see we also get the terms u1 times all of this other stuff. So we get u1 v2, u1 v3, u1 v4, u1 v5 and so on until u1 vn. We also get all the unwanted terms u2 times v1, u2 times v3, u2 times v4 and so on up to u2 times vn. Same with these three and all of the rest. So therefore, we do get all the terms we need, but we also get a lot of the terms that we don't need. So therefore, in general, the sum from r equals 1 up to n of u of r times v of r is not equal to the sum from r equals 1 to n of u of r times the sum from r equals 1 to n of v of r. In addition to these, there is one more rule that we're going to commonly use, and that is the rule for breaking a sum into two pieces. You see, a sum is just all the different values of the thing on the front being added as our indexing variable goes from a certain starting value up to a certain ending value. For our purposes to make this very general, we'll say we'll start at a instead of 1 and we end at, let's say, b. If our term is u of r, then here the sum is going to be all the values of u of r from r equals a up to r equals b. Therefore, this sum is u of a plus u of a plus 1 plus and so on and so forth until the last term, which is going to be u of b minus 1 plus u of b. We can actually break this sum into two smaller sums, and the way that we do it is by considering some intermediate value here and splitting this sum into two pieces. So let's consider that this sum is going to be u of a plus u of a plus 1 plus so on and so forth, but instead of just putting dots all the way until the very last term, let's consider some central term also. So let's say we have a value m which is somewhere in between a and b. So there's going in between the terms of ua and ub, there's going to be a term of u of m. There's also going to be a term after it, which is going to be the term u of m plus 1. And then after that, there's going to be more terms, and eventually we're going to end up back at b minus 1 and u of b. Now, if we consider this sum can be clearly seen to be the sum of all the terms from u of a up to u of m plus the sum of all the terms from u of m plus 1 up to u of b. Due to this, instead of just writing this as the sum from r equals a up to b of u of r, we could break this into the sum of u of r and the sum of u of r as, first off, r goes from a up to m, so r equals a up to m, plus the other sum of u of r terms from r equaling the very first term in our next sum, which is m plus 1, all the way up to b. So r equals m plus 1 up to b. We can see that this effectively splits our sum into two smaller sums. The sum from r equals a up to m of u of r and the sum from the very next term r equals m plus 1 of u of r up to b. So here we can see that we can split any sum starting from one index going up to another index into two smaller sums where the index that we end on the first sum is going to be somewhere in between a and b. And then of course the very other sum, the next sum after that, which contains the term after the r equals m term, is going to start with the r equals m plus 1th term. I should mention that some of you might accidentally write this as r equals m up to b. Don't do this, because if you do this you would be overcounting the term at r equals m. In this sum you would have the sum from r equals a up to m, so it's going to be u of a plus u of a plus 1 plus u of a plus 2 and so on and so forth until u of m, and this sum would also have a u of m term. You would have u of m plus 1, u of m plus 2 and so on. To avoid this, make sure that you do not forget the plus 1 of your index, of your ending index of the previous sum on the next index as starting sum. You might be wondering how this comes in handy. This comes in handy if you have a common formula. Let's say for our purposes we have a formula from r equals 1 up to n of, let's say, u of r, but instead of this what we want is the sum from r equals, let's say, a up to n of u of r. Now we have the common formula for this. We do not have the common formula for this. However, we can find the formula for this if we simply equate these two and say this is equal to this plus the sum from r equals 1 up to a minus 1 of u of r. We can see that with this we have the sum of all the terms from r equals 1 up to a as in a minus 1 and then a and then n of u of r on the right side and the left side. Now if the left side has some common formula for it, we can apply that same formula from r equals 1 up to certain value n for this expression here as well, since we know that this ending term is a minus 1 and we could substitute the formula that we have in terms of n with a minus 1. So therefore, using this technique, if we have formulas of the form r equals 1 up to n of u of r and we have like a common formula for this, we could use this common formula twice in order to find the sum from an intermediate value a up to n. So we will be seeing that in the future soon, but for now what we're going to do next is to solve some simple sums that we can use to solve more complicated sums like these. To start off, the very first sum we're going to be talking about in our list of simple sums that we're going to be using later for more complicated sums is going to be the sum from r equals 1 up to n of 1. Now you might think this is a very simple sum, but it's actually quite important. It is the baseline sum in all of our sums. This sum is the sum of a bunch of 1s from r equals 1 up to n. So we start counting from r equals 1, n counting at r equals n, and for each of those we add a 1. So this sum is just going to be 1 plus 1 plus 1 plus 1 plus and so on, and at last another 1. Now if you consider the total number of 1s here, we have to count from r equals 1 up to n, and for each of those values of r we need to put a 1 over here. So therefore, if you consider counting from r equals 1 up to n, we can see that we will have to count n different numbers between r equals 1 and n. So therefore, the total number of 1s in this sum here is n. You can verify that for yourself. Just take your fingers, start counting 1, 2, 3, 4 and so on. You will see that if you count from r equals 1 up to r equals n, you will count n different numbers. So therefore, our sum here is 1 added to itself n number of times. Repeated addition is multiplication, so therefore this sum here is just n times 1, which is going to be n. So therefore the sum from r equals 1 up to n of 1 is simply n. We can already simply expand this if we consider the sum from r equals 1 to n of k instead. Here we have just one term, one particular setup, let's say one particular specific sum. Here we have a whole family of sums. Now we can find what this is based on this if we just consider the properties of sums that we had earlier. The sum of k times some function, which we could consider as 1 in this case, is simply k times the sum of that function. So therefore this is equal to k times the sum of r equals 1 up to n of 1, which is simply k times n. So therefore the sum of k from r equals 1 up to n is simply going to be k times n. So now that we have this, we can find the sum of any number of numbers from r equals 1 up to n. Now this is quite simple. This is not really all that much to think about, because all we are doing here is repeated addition of the same exact term, and repeated addition of the same exact term is what we call in mathematics multiplication. Hence why there's a multiplication here, and hence why there's kind of also multiplication here. So now that we have established that, let's move on to our next most complex sum. And that sum is going to be, instead of a constant term, it's going to be the sum from r equals 1 up to n of r. We can see we are going up in polynomial steps. Now, how do we sum this? Well, to sum this, let's first consider what this sum is equal to. So if you consider what this sum is equal to, each of the values of r going from r equals 1 up to n, we add r onto the total sum. So therefore, for our first value, at r equals 1, the sum of r is going to be just 1, and then we have to add to that the next value of r, which is going to be the value of r when the value of r is equal to r1 plus 1, which is going to be 2. So therefore, we have 2 here, and then we're going to have to add to that the next value of r, which is going to be the value of r at 2 plus 1 or 3. So therefore, we're going to have to add 3 to that. Then we're going to have to add 4, then 5, then 6, then 7, and so on until we eventually add n. So therefore, the sum from r equals 1 up to n of r is simply the sum 1 plus 2 plus 3 plus 4 all the way up to n. Now, in order to consider what this sum is in terms of a general form that has just n in it, what we're going to do is to consider adding the sum to itself. To do that, what we're going to do is on the left side, consider doubling the sum, and on the right side, consider adding the sum to itself, since doubling something is the same as adding it to itself. On the right side, I'm not going to write the sum as it is up here. I'm instead going to rearrange the sum. It's going to be the same exact sum, but it's going to be rearranged and write it on the next line here. You'll note that a plus b is equal to b plus a, so therefore the order of summation doesn't matter. So what I'm doing here is totally fine. So instead of writing the sum as 1 plus 2 plus 3 and so on until n, I'm going to write it in the reverse order. So therefore the first term I'm going to write is n, the last term I'm going to write is a 1. The term before that would have been a 2, the term before that would have been a 3, and so on in this direction. As for the other direction, this term here is n, the next term after it would be 1 lower, so it's going to be n minus 1, the next term would be another lower, so it's going to be n minus 2, and so on and so forth in that direction as well. So now we have written double the sum of r equals 1 up to n of r, but we've written it in a special way that will allow us to simplify this sum. Now, consider the number of terms here. Same as what we had previously for the sum of 1 from r equals 1 up to n, the total number of terms here is just going to be n. So we have n number of terms here. Now, consider adding each of these term-wise and writing them down here. For the first one, our term is just 1 plus n, so it's going to be n plus 1. As for the next term after that, here we have a 2 and a n minus 1. If we add them together, we have 2 plus n minus 1. We can take the 2 and the minus 1 together and write them as 2 minus 1, and 2 minus 1 is just going to be 1. So therefore, this bit is simplifying to 1, and we have an n additional to that, so we have n plus 1 there as well. If we look at the next term after that, we have a 3 and an n minus 2. Adding them together, the 3 minus 2 is going to give us 1, and the n is going to remain as it is. So therefore, this is also equal to n plus 1. If we keep doing this, we will find that all of the terms here are all equal to n plus 1. The very last term also we can see is going to be n plus 1, which is going to be n plus 1. So therefore, all the terms here are n plus 1, and if we consider the number of terms there are n total terms. Now using this, we can see that the total number of this sum here is going to be n plus 1 added to itself n number of times, which is going to be n times n plus 1. So n times n plus 1 is double the sum from r equals 1 up to n of r. Therefore, we can divide both sides by 2 and say that the sum from r equals 1 up to n of r is simply n times n plus 1 divided by 2. This is a very common result in mathematics. We get it all the time. We use it all the time in summations. It's very useful. It was proven by Gauss. There's a whole story about that. You can click this link in the top right if you want to check that out. But this is our next sum. We can expand this, of course, once again using our same thing from earlier. If we consider r equals 1 up to n of k times r instead, here we can see that this is just going to be k times the sum from r equals 1 up to n of r. So therefore it's just going to be k times n times, actually we don't really need that bracket there, we can just put this like k times n plus 1 divide by 2. Now we are one step higher in our polynomial ladder. We can now represent the sum of r terms in our sum. So we can use this rule and this rule previously already to express the sum of any linear term as a sum which is going to be written as a certain explicit operation of n, a certain explicit equation of n. What I'm talking about here is the fact that now we can write that the sum from r equals 1 up to n of any term of the form ar plus b, we can write this as the sum from r equals 1 up to n of ar plus the sum from r equals 1 up to n of b, which we can then write as the sum for this thing. It's going to be a times the sum of n r equals 1 up to n of r, which is going to be a times n plus 1 divided by 2, and plus this term which is just going to be b times the sum of 1 from r equals 1 up to n, so it's going to be bn. So now we can write the sum of any linear term ar plus b in terms of just n, a and b. The next two sums that we're going to be proving after this are going to be the sums of r squared and r cubed from r equals 1 up to n. For these two, we're going to be needing to use a different technique. This technique is known as a telescoping series or a telescoping sum. The basic idea of a telescoping series or telescoping sum is that when you consider the overall sum, most of the terms in the middle cancel out. An example for this, to give you a better understanding of what a telescoping sum is something like the sum from r equals 1 up to n of a term v of r plus 1 minus a term v of r. In this case, we can see that each individual term is going to be of the form v of r plus 1 minus v of r. If we consider what this sum would be equal to, if we consider evaluating this sum, we can see that if we consider term by term, the very first term would be the value of v of r plus 1 minus v of r when r is equal to 1, which is going to be v of 1 plus 1 over v of 2 minus v of 1. The term after that would be the term v of r plus 1 minus v of r when r is equal to 2, which would be v of 3 minus v of 2. The term after that would be the term when r is equal to 3 of v of r plus 1 minus v of r, which would be v of 4 minus v of 3. This sum would continue on like this until we get to the very last terms. The very last terms here from the pattern we can see, if we consider r equals n minus 1 as in the term before the last term, we would have v of n minus 1 plus 1, which would be v of n, minus v of r, which would be v of n minus 1, so minus v of n minus 1. And the final term would be the value of v of r plus 1 minus v of r when r is equal to n, which would be v of n plus 1 minus v of n. If we consider this overall sum, we can see the first term, the very first term, contains a v of 2. The term after it contains a negative v of 2. From this we can see that this v of 2 and this negative v of 2 would cancel out in our overall sum. Similarly, the second term has a v of 3 in it. The term after that has a negative v of 3 in it. So therefore these two would cancel out. We can see how this would continue with the next term. The term after this term would contain a negative v of 4. So therefore this v of 4 would cancel to that negative v of 4. It would also contain a positive v of 5, which would cancel out for the next term. This would continue on and on and on until we get to the very last terms. Looking at the very last terms, we can see the last term contains a negative v of n. The term before it contains a positive v of n. Therefore, these two here would also cancel out. So this v of n and this negative v of n would cancel out. Considering this previous term, it also has a negative v of n minus 1. From our pattern, we know that the previous term before it would have contained a positive v of n minus 1. Therefore, this term would have cancelled to that previous term. This would continue for so on and so forth for all of the terms, leaving us with just this component of the first term and this component of the last term. Therefore, the telescoping sum contains only this bit, which is v of n plus 1, and then plus this bit, which is negative v of 1, so minus v of 1. We can see that the overall sum of this telescoping sum is limited to only the first term and the last term. We could of course also have telescoping sums where maybe the first two terms and the last two terms get remaining and all of that kind of thing can exist. However, this is the simplest form of telescoping sum, where we get only the last term and the first term's components remaining, and all the other in-between terms get destroyed. So now that we know how telescoping sum works and what it is, we can now see how we can use telescoping sums in order to find the values of the sum of r squared from r equals 1 up to n and r cubed from r equals 1 up to n. It is important when we are doing this to choose a proper telescoping sum that will give us what we want. For the purpose of finding the sum sigma from r equals 1 up to n of r squared, we are going to be using the telescoping sum sigma r equals 1 up to n of r plus 1 cubed minus r cubed. You can see how this would become a telescoping sum if we consider the values involved. If we consider the values involved here, we can see that this sum would be equal to, for r equals 1, we'll make that into like a table so we can see it clearly. For r equals 1, r equals 2, r equals 3 and so on, we'll have certain values. And then on the other side, on the flip side, for r equals n minus 1, we would have certain values, and for r equals n, we would have certain values. Evaluating this thing, we can see we have, for the first term, r plus 1 cubed minus r cubed, which is 2 cubed minus 1 cubed. For the next term, r equals 2, we would have 3 cubed minus 2 cubed. For the term after that, we would have 4 cubed minus 3 cubed, and this would continue downward until the very last terms. For the very last term, we can see for r equals n, we would have n plus 1 cubed minus n cubed, and for the term before that, for r equals n minus 1, r plus 1 would be n minus 1 plus 1, which would just be n, so n cubed minus and then n minus 1 cubed. This term cancels for this term cancels for this term would cancel for the next term. Similarly, this minus n cubed term cancels for this plus n cubed term. This one would have cancelled for this term up here, and so on, leaving us with just the endpoints n plus 1 cubed and minus 1 cubed. So therefore, on the left hand side, the sum here is n plus 1 cubed minus 1 cubed. Now, how does this help us with finding the sum for r equals 1 up to n of r squared, as in the sum of 1 squared plus 2 squared plus 3 squared plus ... until we get to n squared? Well, we can get this result if we simply consider what each of these individual terms is equal to and consider writing this sum in a different way. Here we can see that this sum is the sum of all terms of r plus 1 cubed minus r cubed from r equals 1 up to n. If we consider this internal expression and consider simplifying it, we can see that r plus 1 cubed minus r cubed is simply the expansion of r plus 1 cubed minus r cubed. From the binomial expansion, we know that r plus 1 cubed would expand to r cubed plus 3r squared plus 3r plus 1, and then this minus r cubed would be left as a minus r cubed. We can see here that this plus r cubed and minus r cubed cancel, leaving us with just 3r squared plus 3r plus 1. Therefore, summing together individual terms of the form r plus 1 cubed minus r cubed is same as summing the terms 3r squared plus 3r plus 1. So due to this, we can go up here and say that this sum that we are evaluating, the sum of all terms from r equals 1 up to n of r plus 1 cubed minus r cubed, is the same as adding all the terms from r equals 1 up to n of the form 3r squared plus 3r plus 1, since every individual term is equal. So therefore, we have this equation. We have that now the sum is the sum from r equals 1 up to n of 3r squared plus 3r plus 1. Inside of this, we can see we do in fact have the sum that we're looking for. We have the sum of r squareds. What we have to do now is to separate this into 3 separate sums, which we can do from our rule on summation. We can separate this into the sum of 3r squared from r equals 1 up to n, the sum of 3r from r equals 1 up to n, and the sum of 1 from r equals 1 up to n. Doing so, we can see that this sum is equal to the sum from r equals 1 up to n of 3r squared plus the sum from r equals 1 up to n of 3r plus the sum from r equals 1 up to n of 1. We can simplify a few of these. We can simplify this one and we can simplify this one. For this one, the only thing we can do now is to take this constant factor out from our other rule. So from that we can simplify this line to be 3 times the sum from r equals 1 up to n of r squared, which is the sum that we're looking for, and additional to that we have 3 times the sum of r from r equals 1 up to n, which we know this formula for. I'm going to directly substitute it. It's going to be 3 times n plus 1 divide by 2 and plus the sum from r equals 1 up to n of 1, which we already know to be equal to n. So therefore, taking this equation down here, we can see that from this summation, the sum on the left hand side is evaluated to n plus 1 cubed minus 1 cubed, and on the right side we have 3 times the sum from r equals 1 up to n of r squared plus this bit 3 times n plus 1. Actually, I'll simplify this down to 3n squared plus 3n divided by 2 and plus n. So now we have what we're looking for, and all the other terms are either constants or functions of n. So all we have to do now is to rearrange all of this stuff in order to get an equation in terms of n for this sum from r equals 1 up to n of r squared. Doing so, let's take all of this stuff to this side and write just 3 times the sum of r equals 1 up to n of r squared on the left hand side. We can see if we do that, the sum 3 times the sum from r equals 1 up to n of r squared is equal to n plus 1 cubed, which I'm going to simplify using the binomial expansion as n cubed plus 3n squared plus 3n plus 1, and then there's a minus 1, so we have minus 1, and this term is going to become minus 3n squared plus 3n divided by 2, and this plus n is going to become minus n. So this is what we have on the left hand side and right hand side respectively. We can cut this plus 1 for this minus 1, and we can see we're left with a bunch of terms that all have n in them. Let's now simplify these, try to bring them under a common denominator and evaluate them in a nicer way. So we can see on the left hand side we have this 3 times the sum that we're looking for, sum r equals 1 up to n of r squared. On the right hand side, since we have a denominator of 2 here, I'm going to try to make everything have a common denominator of 2. Doing so, if I take the common denominator of 2, this n cubed becomes 2n cubed, this 3n squared becomes 6n squared, this 3n becomes plus 6n, this thing here minus 3n squared plus 3n, this whole bit remains as it is, so we have minus 3n squared minus 3n, and then this minus n becomes minus 2n when we take it under the common denominator, so minus 2n. Simplifying this down, we can see we have 6n squared and minus 3n squared, that gives us 3n squared. This 6n minus 3n minus 2n will give us n. So therefore, if we actually we can do another step as well. We can divide this 3 out since we have a common denominator of 2. Therefore, we can see that the sum we are looking for, the sum from r equals 1 up to n of r squared, is equal to divide by 6, and on top all we have is 2n cubed, 6n squared minus 3n squared, which gives us plus 3n squared, and then the next term, the constant terms, actually we don't have any constant terms, we have n terms, 6n minus 3n minus 2n gives us plus n, and then that divided by 6 is our sum. We can actually factorize this into nicer factors. We can do that by the fact that we can see, first off, we can remove an n as a factor out of all of these. We have 2n cubed, a 3n squared, and an n, meaning we can take a factor of n out. Doing so, we can see this is equal to the sum from r equals 1 up to n of r squared, which is equal to n times 2n squared plus 3n plus 1 divided by 6. If you take a look at this bit here, we can see we can once again factorize it. Here we can see that the coefficients of the two n's in our factorization, if we had a factorization, would be equal to 2. The coefficients of the other two, the constants, would be equal to 1. As when you multiply them, it would be equal to 1. And when you add them together, you would get 3. If you take a look and you try factorizing this, you can see that you would get factors of 2n plus 1 and n plus 1. Writing that down, we can see that the sum here, the sum from r equals 1 up to n of r squared, is equal to n times n plus 1 times 2n plus 1 divided by 6. You can see that this is true because if you multiply through this thing, we have n times 2n, which gives us the 2n squared. We have n times 1, which gives us one of the n's. We have 2n times 1, which gives another 2 of the n's, leading up to a total of 3 n's. And if you multiply the 1 and the 1, you get the 1. So therefore, this is the fully factorized form of the sum from r equals 1 up to n of r squared. With this, we now have a common form, a common way to write the sum of any quadratic sum, as in of the form ar squared plus br plus c. So we can generally write, if you have the sum from r equals 1 up to n of ar squared plus br plus c, we can actually find this thing in terms of a general form of just n. We can write this as going to be equal to a times the sum of r squared, which is going to be n times n plus 1 times 2n plus 1 divided by 6, plus the sum of b times the sum of r, which is going to be b times the sum of r, which is going to be n times n plus 1 divided by 2, plus the sum of the constant term c times the sum of 1, which is just going to be c times n. So therefore, this is the common general form for the sum from r equals 1 up to n of ar squared plus br plus c. The next and final sum of this form that we're going to be considering in this video is going to be the sum from r equals 1 up to n, the sum from r equals 1 up to n of r cubed. You can of course go further, you can go to r to the power of 4, r to the power of 5 and so on. However, we only go to r to the power of 3 within our syllabus. That's all you're going to be questioned with, and most likely you'll never be questioned with anything higher than r squared. So anyway, let's try and figure out how we can find the sum from r equals 1 up to n of r cubed. Once again, as I hinted to earlier, we're going to be using a telescoping sum. To find the sum of r cubed, we're going to be using the telescoping sum sigma r equals 1 up to n of r plus 1 to the power of 4 minus r to the power of 4. In general, if you want to find the sum of r to the power of, let's say, k, you can do it by finding the telescoping sum of r plus 1 to the power of k plus 1 minus r to the power of k plus 1. So anyway, going to this telescoping sum, if we consider the terms involved and do that same left side, right side simplification that we did earlier, we can see that for r equals 1, r equals 2, let's do r equals 3 as well, and then let's skip ahead to r equals n minus 1 and r equals n. If we consider the terms involved, for r equals 1, we're going to have 2 to the power of 4 minus 1 to the power of 4. For r equals 2, substituting, we would have 3 to the power of 4 minus 2 to the power of 4. The next term would be 4 to the power of 4 minus 3 to the power of 4. Going down, for the last few terms, the last term would be n plus 1 to the power of 4 minus n to the power of 4, and the term before that would have been n to the power of 4 minus n minus 1 to the power of 4. Considering the telescoping sum, we can see that all of these intermediate values cancel out. This 2 to the power of 4 cancels to this 2 to the power of 4, this cancels to this cancels to that, and so on. If we consider the other direction, this n to the power of 4 cancels to this one, this cancels to this, and so on, leaving us with just n plus 1 to the power of 4 and minus 1 to the power of 4. Writing that down here, our final sum on the left hand side would be n plus 1 to the power of 4 minus 1 to the power of 4. Now, once again, we're going to be considering another way to write this down, and by doing that, we're going to isolate the sum from r equals 1 up to n of r to the power of 3. So, let's go down and figure out what our sum is going to be, and using that, let's isolate the r to the power of 3 summation. Considering r plus 1 to the power of 4 minus r to the power of 4, r plus 1 to the power of 4 can be expanded using the binomial expansion as r to the power of 4 plus, it's going to be 4 r cubed plus 6r squared plus 4r plus 1. This can be found using the binomial expansion and the choose function. And then on the end, we're going to have a minus r to the power of 4. We can see that this will cancel to this, leaving us with just the sum 4r cubed plus 6r squared plus 4r plus 1. Now, if we consider this thing and we go up over here and we substitute this thing into here, we can see that the sum of r plus 1 to the power of 4 minus r to the power of 4 is equivalent to summing from r equals 1 up to n the sum 4 times r cubed plus 6 times r squared plus 4 times r plus 1. Once again, we're going to be using the same technique of breaking this into pieces and substituting all of the sums that we know so far, which is the sum of r squared, r and 1. So doing so, we can see, I'm going to skip the step where we have the coefficients on the inside of the sum. I'm just going to take them out directly. This is going to be 4 times the sum we're looking for, the sum from r equals 1 up to n of r cubed, plus 6 times the sum from r equals 1 up to n of r squared, plus 4 times the sum from r equals 1 up to n of r, plus the sum from r equals 1 up to n of 1. Now, most of these we can substitute. We can only not substitute this final sum, which is the sum that we're looking for. Writing the rest of them down, we can see this is equal to 4 times the sum from r equals 1 up to n of r cubed, plus 6 times this sum, which we know to be n times n plus 1 times 2n plus 1 divided by 6. You can see the 6 and the 6 nicely cancel out. As for the next one, this is 4 times this sum, which is going to be 4 times the sum, which is n times n plus 1 divided by 2. This divided by 2 and this 4 cancel to give us just a 2 here. As for the last bit, this is just the sum from r equals 1 up to n of 1, which, it's the simplest one we proved. It's just n. Now, taking all of this down, we can see that our sum, the sum that we're looking for, times 4, so 4 times the sum of r equals 1 up to n of r cubed, plus all of this stuff, which is going to be n times n plus 1 times 2n. We can actually simplify this down. We can simplify this to 2n squared plus 3n plus 1 plus 2n squared plus 2n plus n is equal to n plus 1 to the power of 4 minus 1 to the power of 4. Now you know the drill at this point. What we're going to do is simplify everything, rearrange, and we're going to get an equation for this bit in terms of only n. So doing so, the next step here would be to expand this thing and simplify by taking this bit only to one side. So we're going to do that. We're going to take this to one side and write this is equal to 4 times the sum from r equals 1 up to n of r cubed, which is equal to all of this other stuff on one side. We're going to have n plus 1 to the power of 4 minus 1 to the power of 4. If we expand n plus 1 to the power of 4, is going to be n to the power of 4 plus 4n cubed plus 6n squared plus 4n plus 1. And then there's going to be a minus 1, so minus 1. And then there's going to be all of this stuff minus and all of this stuff minus. Expanding this stuff out, we can see we have minus 2n cubed minus 3n squared minus n, and here we have a minus 2n squared minus 2n and another minus n. Now, if we consider simplifying all of this, we can see we have a plus 1 and a minus 1 which can cancel. We have a minus 2n, a minus n, and a minus n here. So we have minus 4n in total, which can cancel for this plus 4n. Where we can also see we have a plus 4n cubed. Here we have a minus 2n cubed, which we can cancel out to just have a single plus 2n cubed. And we can see we have 6n squared, a minus 3n squared, and a minus 2n squared, which cancels to just give us a single plus n squared. Simplifying all of this down, we can see our sum is equal to 4 times the sum from r equals 1 up to n of r cubed, which is equal to n to the power of 4 plus 4n cubed minus 2n cubed, which is going to be plus 2n cubed, and this plus 6n squared minus 3n squared minus 2n squared is just going to give us a plus n squared. Now, if we start factorizing this, we can see that all three of these terms have an n squared inside of them, so we can factor that out. Doing so, we can see we have 4 times the sum from r equals 1 up to n of r cubed being equal to n squared times what's left over, which is going to be n squared plus 2n plus 1. So we have n squared plus 2n plus 1. We can see that this can actually be factorized further by the fact that n squared plus 2n plus 1 is simply n plus 1 squared. So we have 4 times the sum from r equals 1 up to n of r cubed being equal to n squared times n plus 1 squared. Now we can see that finally our sum, the sum we're looking for, the sum from r equals 1 up to n of r cubed, is equal to n squared plus, so times n plus 1 squared divide by 4. I'm going to write this divide by 4 as a divide by 2 squared, because if we do that, we can see that this whole thing is a square number. It is n times n plus 1 divided by 2 whole thing squared. Therefore, the sum from r equals 1 up to n of r cubed is equal to n times n plus 1 divided by 2 whole thing squared. You can see a nice interesting thing that happens here, because the sum from r equals 1 up to n of r is equal to n times n plus 1 divided by 2. Because of this, we can say that the sum from r equals 1 up to n of r cubed is equal to the sum from r equals 1 up to n of r whole thing squared. It's a nice interesting result that we get when we simplify this thing down and find this expression. So you can say the sum from r equals 1 up to n of r cubed is equal to the sum from r equals 1 up to n of r whole thing squared. It's a nice interesting result that we get when we do this. So now that we've gotten up to this point, if you ever find a sum like of the form sum from r equals 1 up to n of a r cubed plus b r squared plus c r plus d, you can easily find this sum's expression in terms of just n, using all of the identities that we've proven above. Now that we've done that, our next bit, our final bit in this video here, is going to be discussing the sums of arithmetic series and geometric series. Let's first discuss arithmetic series. Arithmetic series, also known as arithmetic progressions. The idea of arithmetic progression is that you have some starting term a, and every term after that is the previous term plus some constant value, which we usually represent with d. So the next term after the a would be a plus d. The term after that would have another plus d. It would be a plus 2d. The term after that would be a plus 3d, a plus 4d, and so on. And the nth term would be a plus n minus 1 times d. So if we consider going forward like this n number of times, the last term would have a total number of d's being equal to n minus 1, as I think we would have n minus 1 d's added to our initial a, meaning that the last term, the nth term, would be a plus n minus 1 times d. Occasionally, we will write this as just being the last term, and we will occasionally write it as being L, as in the last term is simply represented by L. So therefore, an arithmetic series could also be written as a, comma, a plus d, comma, a plus 2d, and so on from this direction. And on the other side, we could write it as being the last term, and then the last term minus d, the last term minus 2d, and so on that direction as well, since each progressive term needs to be d greater than the previous term. So therefore, this is what we mean when we talk about an arithmetic series or arithmetic progression. It's a series where each term is d greater than the previous term, and we have some starting term or some ending term. Now, given this kind of series, the sum of this kind of series is just all of these terms added together. So therefore, when we talk about the sum of an arithmetic series, we're just talking about a plus d plus a plus 2d plus so on and so forth until the last term, which is going to be L minus 2d plus L minus d plus L. Now, there is actually a nice way to write each of these sums in terms of the first term and the last term. So let's go over the sum of this series in terms of just the first term and the last term. In order to do that, what we're going to do is to consider the sum s as being s equals a plus d plus a plus 2d and so on until L minus 2d, L minus d, and L. And then we're going to consider this sum s equals, and what we're going to do is to just rotate this thing the other way around. So we're just going to, instead of writing all of these terms in this order, we're going to write them in the reverse order, as the first term being L, the term after that being L minus d, the term after that being L minus 2d, and so on, all the way down. On the other side, we're going to have this term being a plus 2d, the term after that being a plus d, and the last term being just a. Now, if we do this, we can see an interesting pattern. We can see that if we add these two, we can get a plus L. If we add these two, we can see we have a plus d and l minus d. The plus d and minus d cancel, once again giving us a plus l. You might notice that this is almost the exact same as the way that we used to find the sum of r from r equals 1 up to n. And you're right, this is almost the same. It's just that instead of going up in increments of 1, we're now going up in increments of d. The logic still works the exact same, it's just that the formula that we get is slightly different. Here we can see for the next term, the plus 2d and minus 2d cancel, once again giving us a plus l. From the other side also we can see we have a plus l and a plus l all the way through. So here if we consider 2s is just a bunch of a plus l's added together. So we have a plus l plus a plus l plus l plus another a plus l and so on. And on the other side also we have a plus l plus a plus l and so on until the very last term, which is also a plus l. If we consider the total number of a plus l's that we have here, if we had n number of terms from start to finish, then we have 1, 2, 3, 4, 5, so on and so forth until n minus 1 and n total number of terms. So therefore, if you consider the total number of a plus l's that we have here, there are n number of a plus l's that we have added together over here. So therefore, the total sum s or 2 times s is going to be n times a plus l, meaning that the total sum s is going to be n times a plus l plus l divided by 2. So there we go, we have a sum of the form n times the first term plus the last term divided by 2 for an arithmetic series where the first term is a and the last term is l. You'll note that we don't really care what the d is here because it's encoded inside what the n is. The total number of terms and the first term and the last term also encode the difference of d between each consecutive term. We can of course write this another way. If instead of the last term we want to just have a, d and n being the parameters that give our function, we can do that as well. We can do that by considering what L is based on our definitions of the terms. Here we can see if we define L like this, L is the last term. If we instead consider L in terms of A and D, we can say that L is equal to A plus n minus 1 times D. Therefore, we could go back into this formula here and we could substitute L for A plus n minus 1 times D. Doing so, we can see that this sum is also equal to n divided by 2 times A plus the value of L, which is going to be A plus n minus 1 times D. So therefore, this is also a valid formula for the sum of an arithmetic series. It's just that in this formula, we only have A and D. If we clean this up, we can add these two A's together, leaving us with just with S equals n times 2A plus n minus 1 D divided by 2. We could even, take this 2A divided by 2 and this n out and write that a separate thing as in n times A plus n times n minus 1 times D divided by 2 as well. But I think this is an alright format for our sum. So therefore, the sum of an arithmetic series can either be written as the total number of terms times the first term plus the last term divided by 2, or it could be written as this formula that we have here. So that is the formula for any arithmetic sum. So we could do something like, for example, let's say the sum 5 plus, let's do 5 plus 8 plus, we can do next 11 plus and so on and so forth. Let's say we go up to 65, right? So if we go up to 65, and we have to ensure, of course, that this is an arithmetic sum, we can do that by just considering the terms mod, in this case mod 3, because here we are going up in increments of 3. Here we have plus 3, here we have plus 3. If we consider the terms mod 3, we can see that this is in fact a valid geometric series, arithmetic series, because this last term is also equal to 2 mod 3. So anyway, this is a valid arithmetic series. If we consider the arithmetic progression and we consider the values involved, the difference D is equal to 3, or we could consider the first term and the last term. If we consider the first term and the last term, the first term is 5, the last term is going to be 65. If we consider the total number of terms involved, we are going to have 5, 8, 11, we're going up by 3 each time. From the first term to the last term, we can see we've gone up by 60, which is 23s, meaning that there are 21 total terms in this sum. So we have 21 total terms. The first term is 5, the last term is 65. Therefore, the sum here, S, is equal to 21 times the first term A plus the last term, which is L, so 65, divided by 2, which is equal to 21 times 5 plus 65, which is 70, divided by 2, which is going to be 35. Writing this out, we can see that 20 times 35 is going to be 700, and 1 times 35 is going to be 35. So therefore, our answer is 735. We can see, instead of doing the whole sum manually, we can once again, using sigma notation and our idea of an arithmetic series, easily find the sum from r equals 1 up to n. If we wanted, we could have reduced this also into a form of sigma ar plus b or something like that, in which case the a would be the as in the starting value would be our first thing, and then the d would be 3, as in if we wanted to write this thing in terms of sigma notation with r and constant term, it would be the sum from r equals 1 up to n of dr, since we want to go up by r each time, plus actually r minus 1, since the first term is not going to have any ups and downs from our starting value, and plus a. This would be the sigma notation way to write this arithmetic sum here. We could also, of course, easily use either of these formulae to find the sum. Moving on from that, the final sum that we're going to be discussing is called the sum of a geometric series. A geometric series is defined by the fact that we have a first term, and every term after that is a particular ratio times the previous term. So if we consider the first term to be a and the ratio to be k, then the term after that is going to be multiplied by k from the previous term. So the first term is a, then the next term is going to be a times k. The term after that is once again going to be multiplied by k from the previous term, so it's going to be a k squared. The term after that is going to be a k cubed, and so on and so forth until the very last term. If we consider that this series has, let's say, n number of terms, then we can see from the pattern that the very last term is going to be a times k to the power of n minus 1. Since the second term is k to the power of 2 minus 1, the third term is k to the power of 3 minus 1, and so on. The last term in the series, which has n number of terms, is going to be a times k to the power of n minus 1. The sum of such a series can be easily found if we consider multiplying the whole series by k. I'll show you how that happens. If we consider, let's say, s equals a plus ak plus ak squared plus and so on and so forth until a k plus a k to the power of n minus 1. If we consider k times s would be all of the terms here, each being individually multiplied by k. So we'd have ak here, the next term would be ak squared, term after would be ak cubed, and so on and so forth until the last term, which would be a times k to the power of n minus 1 times k, which would be a k to the power of n. So therefore, k times the sum that we're looking for is going to be equal to this. Now, let's consider subtracting this first sum from the second sum, as in we're going to consider ks minus s. If we consider ks minus s, we can see that the second sum has an ak, the first sum also has an ak, so this would cancel to this. The second sum has an ak squared, the first sum has an ak squared. When you subtract, that would cancel to that. If we consider the next term, we have ak cubed here, we can see how we would have an ak cubed here, so this would also cancel. If we consider the last term, we can see that while the last term here is ak squared, there would actually be a term before it with ak to the power of n, there would actually be a term before it which would be of the form ak to the power of n minus 1. Therefore, this term would cancel to the very last term in our series above. From this we can see that our series simplifies to just ak to the power of n minus a. So our series is just a times k to the power of n minus a. If we consider this, we can see on the left hand side we can factorize this as being k minus 1 times the sum, and on the right side we can see we can factorize this as being a times k to the power of n minus 1. Now we can see that if we divide both sides by k minus 1, our sum s is equal to a times k to the power of n minus 1 divided by k minus 1. It is important to note here that we should not allow k to be equal to 1. If k was equal to 1, we would have a 0 divided by 0 issue here, and therefore our sum would not be given by this particular formula. If k was equal to 1, however, of course, we can find our sum in a different way. If k was equal to 1, then every single one of these terms would be equal to a, since multiplying by 1 does nothing. So therefore ak would be the same as a, ak squared would be the same as a, all of the terms would be the same as a. In which case, we just have a total of n number of a's being added together. Therefore, in that case, the case where the value k is equal to 1, we can see how our total sum would be just a times n. So in the case where k is equal to 1 is just a times n. In the cases where k is not equal to 1, we can see that our sum is going to be s equals a, which is the first term, times k to the power of n minus 1 divided by k minus 1. So there's our sum for a geometric series. We can be expected to use all of the sums in this video in various different applications, in various different questions that we can find in our papers. So therefore, I highly recommend that you take each of these certain sums, either make your own question and try to solve it, or find past paper questions and solve those questions using each of these sums, and by applying them, you can better understand them and better remember them for when you're going to use them in the actual exam. So that's going to be it for this video. I hope you enjoyed. Thank you for watching, and goodbye.